Hello, today's video is on spherical coordinates. And, well, I don't know this for fact. I'm pretty sure it was invented just for Gaussian integrals. And realistically, probably not, but this is the only case where I see spherical coordinates used is in Gaussian integrals. So, since Gaussian integrals are used throughout statistics, I think it's worth knowing the development of this coordinate system. And we're going to do it going from R2 space to R3 to R4, so you can kind of see the general development, and then we'll give an example at the end. In R2 space, the spherical coordinates are an ordered tuple, R and theta 1, where R is positive and theta is between 0 and 2 pi. So if you can think of it as in this picture, that we have a coordinate system, x1 and x2, and some point in space. Then that point, and so this is the origin. And so if we draw a point from the origin to that point, then it creates an angle, but with theta, or the x1, right? And it could be anywhere from 0 to 2 pi. And then the distance from that point is r. And then that's all we need to describe a point in 2 space. And a note is that this is equivalent to polar coordinates, except that r can only be positive. In polar coordinates, you can have a negative value. Now, here's another note that will seem silly initially, but I'm going to keep pointing it out to you, and then in R4 space, you'll go, oh, that's why he was doing it. If we get rid of R2 space, X2, we don't need X2 to create that angle, right? There's some axis, X1, and some point, and on X1 there's an origin. And we can draw a line from the origin to the point and create that angle, regardless of X2. We don't need it to create X1. Now, we need X2 to know distance, and etc. So, to know X1, we only need this triangle. We don't need X2, right? Because the cosine of theta 1 is this X1 over R, and then you can kind of back solve for X1 and you get this. Now X2, it would be the sine of this angle, which is this distance over radius. You can kind of back solve and get this. So this is how you go from spherical coordinates back to the Euclidean system, or the XY plane, Cartesian coordinate system. And then if you plug in what we know for X1, then X1 plus X2 is R squared, that distance. Now the Jacobian of the transformation it's the partial of X1 with respect to R. This is partial of X2 with respect to R. Partial of X1 with respect to theta 1. Partial of X2 with respect to theta 1. Maybe I said theta 2, theta 1. And then you take the determinant and you get this. And then it's actually the absolute value, and it's R. We get, right? So if you factor out an R here, you get cosine squared plus sine squared, and that's 1, so you get R. Now let's move to 3 space. Ordered triples, R, theta 1, theta 2, where R is positive or non-negative, and theta 1 is between 0 and pi, and theta 2 is between 0 and 2 pi. So here's the picture of what's going on. So our system, x1, 2, and 3, there's some point in space. Then R, of course, is the distance from the origin. Theta 1 is the angle from x1, and theta 2 is the angle from x2. So now if we think about that, and these have actually names, zenith and polar angles, and I'm butchering those names, but they all have specific names based upon the angle at which it creates with the axis, and you'd have to look that up. So now for R, of course, it's wherever, it's a line from the origin to that point. It's the distance from that point. But for x1, now, and this is the silly part, I can cover up the other axes, right? And this angle that it creates is theta 1. Now, this kind of could rotate around theta 1 and never be more than pi. That's what this says, right? So if the angle's down, then it's more, it's almost pi. If it's straight down, it's pi. So we don't need the other axes to create this angle. But now when we project this down into the x2, x3 space, that's where we get our x2 and 3 coordinates. So here, to get x1, we just need the cosine of theta 1, which is this over that, and you kind of back solve for x1. Now, q, when we project this down, right? So this axis and this line are parallel, and we know this distance is r, and when we project it down, this is a right angle, right? And so and this is a transversal, so alternate interior angles are equal, so this angle is theta 1, and so the sine of theta 1 is q over r. And then you can back solve for q, and you get this. Now, why is that important? Well, if we know q, then this angle is helpful, because this angle is theta 2, and we want to know this, so the cosine of theta 2 is q over, and now this is a right angle, no, it's x2 over q, and you can kind of back solve for x2. But q, we said, was this, so you can plug it in and you get this relationship. Now x3 is this distance, so you can take the sine of theta 2, and it's this distance over q, so then you can kind of back solve and get x3. But q was this, so you plug it in, and then there's our switch to Cartesian coordinate system, these angles. So now another note is that if we plug in those values that we achieved and square them, which is this, you can kind of solve it and we get r squared. So the Jacobian of this transformation, remember, now this is x1 and this is x2 and this is x3. And so if you want, you can use this is actually what we needed to find the Jacobian on. But since I have to flip it over, we can kind of look at this, x1, x2, x3. So here, this is the partial of x1 with respect to r, partial of x2 with respect to r, partial of x3 with respect to r. These are with respect to theta 1, and these are with respect to theta 2. And notice this is 0, right? Because there's no theta 2 in the x1 component. Now, let's take the Jacobian, and I'm going to traverse across this row because it's 0. We only have to do it twice. And so it's this times the Jacobian of that, which is this. Then it's minus this times the Jacobian of that. You get this. And so you can kind of solve that, and you get r squared times sine of theta 1. And in our example, this is going to come back in. So theta 4 is an ordered 4 tuple, r1 through theta 1, 2, and 3, where theta 1 and 2 are between 0 and pi, theta 3 is between 2 pi. Now this development, remember I said in the previous two examples, I said we don't really need the axes, the other axes, except for x1, to find the value x1, right? Because it makes an angle with this axis. And so if we take the cosine of theta 1, we get this over r, and you can kind of back solve for x1. Now what we're going to do, this is in 4 space, you can't really graph it. So what we're going to do is take this and project it down onto x2 and x3. So this is the next picture. So this, this piece is from the, what we did on the last page. Now we're projecting it down into x2 and x3. So the same thing. So this is an axis 1, and this is parallel to axis 1. Wherever it is in space, it's parallel. And then, and so this is alternate interior angle. So this is theta 1, and this comes down and makes a right angle with this plane. So the sine of theta 1 is q1, this distance, over r, and you kind of back solve for q1, and you get this. So, but now you know q1, we can use that for this angle, because this angle, and I don't know why I didn't write it, is theta 2. So the cosine of theta 2 is x2 over q1, and you can kind of back solve for x2, but q1 we said was this, and so you can plug it in, and this is this is how you find x2. Now x3 this is the interesting one. Now this is in the x2 x3 plane. We're going to project that down to the x3 x4 plane. Okay, so essentially what we're doing, taking this and rotating it somehow, making it, north-south, and then the x3, x4 plane is here. But remember, this distance is q1. So this distance is q1, because we're in the x1, 2, 3 world. So, so to find theta 3, we project it down. Now this is parallel to this, right? So these are alternate interior angles. So this is theta 2, right? So theta 2 is this distance over this angle, right? This is the hypotenuse of this triangle. So you can kind of back solve for q2. And so q2 is q1 times sine of theta 2, which is this angle. Now to find 3, right, we know this is q2, and we want to find x3 here. So it's the cosine of theta 3 is this over q2. And you can kind of back solve for x3, right? But q2 was this, and then q1 was this up here. So you can kind of put all those pieces together and you get this. Then x4 would be the sine of this angle, because it's this distance, which is this distance. Back solve and you plug it in, and you get this. So this is x4. So now the interesting part is, if you plug in x1, 2, 3, and 4, these values in for this, it simplifies to r squared, right? So this is one of the reasons we use spherical coordinate, because when we plug it in, it simplifies to just a number. Really easy to integrate. So now the Jacobian, and I couldn't, this is a 4x4 matrix, so I couldn't put it all on the same page. So this is the partial of x1 with respect to r, partial of x2 with respect to r. These partials are with respect to theta 1, theta 2, theta 4, and I'm going to let you go through that on your own. And then to take the determinant, you get this, r cubed sine of squared of theta 1 sine of theta 2. Now, to generalize this, in Rn space, it's an n-tuple, which is this, and r is non-negative. Theta 1 through theta n minus 2 are between 0 and pi, and that last one is between 0 and 2 pi. And you'd go through the same approach that we just did, and then you would come up with this system. X1 is this, X2 is this, X3 is this, so X4 is this. So really it's R, and then it's sine, and the last one's a cosine, right? And Xn is the same except for it's a sine. And this is the same relationship we got in X2, 3, and 4. If we plug in these values for X1 squared through Xn squared and then simplify it, it knocks down to R squared, which is easy to integrate. The Jacobian is this. So whatever space we're in, it's 1 minus that for R. Then it's 2 minus it for the sine of theta 1, theta 2, and all the way to the sine of n minus 2. As an example, let's say we want to integrate this Gaussian integral. Now I have a video called Gaussian integrals if you want to see what the value of this is and the approach we used in that video. But here we're going to change it to spherical coordinates. So if we plug in what we know for x1, 2, and 3 in spherical coordinates, it all cancels to R squared, right? And then we need to take it times the Jacobian of this transformation in R3 space. So now let's integrate it over theta 1, and so the antiderivative of that is minus cosine of theta 1, and we're integrating it from 0 to pi. And so this is pi is minus 1, so it's minus 1 minus a minus 1, which is 1, minus this times that, which is 1, so we get 2, right? So this 2 is here, and now we want to integrate the second one with respect to theta 2, but there is no theta 2, so then the antiderivative is theta 2, and you plug in these values and you just get 2 pi. So you take 2 pi out, and that's how you get the 4 pi. Now we integrate this with respect to R, but we make a u substitution, let u equal R squared. R is then u to the 1/2, du is equal to 2R dr. And then you plug everything in, you get this integral. But this is a gamma integral, so we instantly know that it integrates to this. We simplify. This is 1/2 times the square root of pi, so the 2's cancel, the 1 goes away, square root of pi goes into this, and you get pi raised to 3/2 power. Well, that's exactly what we got in my video called Gaussian integrals. Well, anyway, I hope this helps with the development of spherical coordinates. You often don't see it developed in 4 space, so I hope that's kind of a new approach for you. Well, that's all I have. Hope you liked it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.